Hello all, this is Hasiba. Welcome to today's session. So today we'll be discussing the next lab program. So in today's session we are discussing program number 7. The program number 7 is to recursively subdivide a tetrahedron in order to form a 3D Sierpinski gasket. Right, so that means we are considering a tetrahedron and we are recursively subdividing a tetrahedron so that we get our 3D Sierpinski gasket. So the 3D Sierpinski gaskets look something like this, right? So as the number of division increases, right, so you will have a picture somewhat of this shape. Fine. So before going into 3D Sierpinski gasket, we'll first understand what do we mean by a tetrahedron. So a tetrahedron is also known as a triangular pyramid, right? So you can see here, it is just the shape of a pyramid shape, right? So which consists of how many faces? It consists of 4 triangular faces, right? So you can see we have a face with blue color, we have a face with red color, we have a face with black color, and the other face is the bottom face, right? So a tetrahedron is a triangular pyramid, or it is a polyhedron which is consists of 4 faces, and it consists of how many vertices? It consists of first vertex, right? So this, if I take the from the top view, you have to see from the top. If you see from the top, this is your first vertex, this is the second vertex, this is the third vertex, and this is the fourth vertex, right? So you have 4 vertex corners, you have 4 triangular faces, and how many edges we have, right? So start counting the edges. This is the first edge, this is the second edge, you have third edge, fourth edge, fifth edge, and sixth edge, right? So a tetrahedron consists of 6 edges, 4 vertices, and 4 triangular faces, right? So it is also called as a triangular pyramid. So in this program, what we have to do is we have to draw a tetrahedron, right? And we have to recursively subdivide that particular tetrahedron so that we get the shape of a Sierpinski gasket, right? So it is in order to form a 3D Sierpinski gasket, we are subdividing a tetrahedron in this particular program. So let us have a little bit insight about what is a 3D Sierpinski gasket, right? So it is basically an application of fractal geometry. That means a fractal geometry, it is a concept, right, which is constructed by a recursive procedure. That means we take a triangle, we further subdivide the triangle, right? So again, that particular triangle will be divided. The parts of the triangle will be further divided into again in smaller triangles like that, right? So recursively we will be dividing each triangle into 4 new triangles. Every time the triangle will be divided into 4 new triangles, right? So again the central triangle is removed, and again each of the 3 are treated as the original one, and again the division happens, right? So we are performing the infinite divisions here in a finite space. So within this particular space of the triangle itself, we are going for a infinity number of divisions, right? So this 3D Sierpinski gasket, it was named after is a Polish mathematician by name Wada Sierpinski, right? So in 1970. So this 3D Sierpinski gasket, it is basically an application of fractal geometry, right? So what is the fractal geometry concept? It is nothing but consider a triangle and divide it into 4 new triangles, again division, right? So that is the concept of your fractal geometry, right? Now coming to our lab program, right? So this is our original tetrahedron with number of divisions as 0, right? So that means I have not divided this particular tetrahedron. If I take number of divisions as 1, right? So I will be getting how many tetrahedrons? You can see here, see from the top view, I'll be getting 1, 2, 3, and 4, right? So the original tetrahedron is divided into 4 tetrahedrons. You can see here, this is one tetrahedron, the first one, this is the second tetrahedron, next third tetrahedron, and fourth tetrahedron. Like that, your single tetrahedron will be divided into 4 tetrahedrons, number of divisions as 1. If your number of divisions increases, right, so the number of tetrahedrons what you get also increases. So let us start. Let us try to understand our lab program now. So the first statement in our lab program is hash include stdio.h, right? So this is including your standard input output header file, because in this program I'll be making use of my printf and scanf functions in order to read the number of divisions. So next I have hash include gl/glut.h, right? So this is basically our glut header file. Next we have declared one variable, right? So one array variable which is called as point of 3, right? Because here I'm considering a 3D polygon, right? So whenever I have a 3D polygon, my point consists of how many coordinates? It consists of x coordinate, it consists of y coordinate, and it has z coordinate. Since a point consists of x, y, and z coordinate, so I have to take an array of 3 points, right? And this particular array, I'm type defining the float data type as the point of 3 array, right? So wherever I take the point, that means that I'm taking it as a float data type, right? So next step is we are writing the vertices of our tetrahedron. How many vertices were there in our tetrahedron? Our tetrahedron had 4 vertices, right? So the center is the vertex 0, then vertex 1, vertex 2, vertex 3. So how to write these array? Right, so in order to write this array, so just take the point data type, point v of 4 is equal to, right? So coming to this point, so this is our first point, which is the origin, right? So in this origin, if it is origin, x is 0, y is 0, and since I'm viewing from the top view, right, so which is my front face, so whenever I'm considering the front face, right, so my z-axis will be positive, right? So that is why I'm taking the value here as 0 comma 0 comma 10. You can take it as 10, 20, anything, that is your wish, right? So but it will be positive because you are seeing from the front side, or it is the top view, so it is positive z-axis. The next vertex is v1, right? So you can see that v1 is located on the y-axis, right? So on the y-axis, we know x is 0, right? So and I am taking y as a 10, right? And this is my bottom face because I am seeing from the top view. So this vertex v1, vertex v2, and vertex v3 will be down, right? So since they are at the bottom face, they will come under negative z-axis, right? So I will write it as 0, 10, minus 10. 0 because it is on y-axis, x is 0, right? So y is a 10 because the point is located somewhere here, right? And z is minus 10. Coming to the next vertex, so this vertex is located in negative x and negative y quadrant, right? So since it is negative x and negative y, I will take it as minus 10 comma minus 10, right? And since again it is the bottom face, I will take my z-axis as negative, so minus 10. Coming to the last vertex is located in positive x and negative y, right? So since it is positive x, I will take it as a 10. It is negative y, right? So I will take it as minus 10, right? And since it is at the bottom face, the z-axis will be negative, right? So like this, you have to define the vertices of your tetrahedron. So these vertices you will be writing in your vertex array, which is v of 4. 4 vertices of the tetrahedron are defined. So next we are using one variable called as m. So this variable m will hold the number of divisions. How many ways you want to divide your tetrahedron. So number of divisions variable is m, right? So next, as we can see, what is a tetrahedron? A tetrahedron is nothing but a combination of 4 triangular faces, right? So every face of the tetrahedron is actually a triangle. That means I have to draw this triangle. Again, I have to draw, considering these vertices, I have one triangle, right? I have to draw this triangle, right? And I have to draw one more triangle, which is my bottom face, right? So that's why I'm using a function. The first function what I'm using is a triangle function. So void triangle. So every triangle has how many points? It has 3 points. So point A, point B, and point C, right? So in order to draw a triangle, we have to make use of our GL underscore polygon, right? So we'll be using our begin and end primitive in order to draw our triangle, right? So GL begin, GL underscore polygon, it has 3 vertices and it is in terms of 3 dimension. So that's why I'm taking GL vertex 3F, right? So it is float vertex. The point vertex is a type of, the point array is a type of a float vertex, right? And it is 3 dimension. That's why GL vertex 3FV of A, right? Because the first point is A, next B, next C, right? So a triangle can be drawn by making use of 3 points A, B, C, and finally I'm making use of my end primitive. Now coming to the next function. So next function is to divide a triangle, right? So in order to divide a triangle, since it is a triangle, I need 3 points. So point A, point B, point C I will be taking, and one more variable I'm taking here, which is called as m, because m is a variable which is holding the number of divisions, right? So then I need 3 points. So point P1, point P2, point P3. I'm using one more variable which is called as I. So this I variable is basically used for indexing variables. So now if m is greater than 0, right? So if the number of divisions are greater than 0, if the number of divisions are equal to 0, then I will get my tetrahedron which is not at all divided, right? So we are getting our basic tetrahedron as output. If at all the number of divisions increase, right? So then I have to divide my each face of the, I have to divide each face of my tetrahedron. In order to do that, right, so we know that every face of the tetrahedron has how many vertices, right? It is, since it is a triangle, every face of the tetrahedron is actually a triangle, right? So a triangle means it will have three vertices, right? So I will take it as vertex 0, vertex 1, vertex 2. Therefore my for loop I am taking it as for I equal to 0, I less than 3 and I plus plus. For I equal to 0, I less than 3, I plus plus. So what we are doing here is, in order to divide the triangle, we have to find the midpoints. So point P1, point P2, point P3 are actually the midpoints for each and every edge of the triangle, right? So I'll consider one part of the face, as you can see here, right? So I'm taking here, this is my tetrahedron vertex 0. This is my, so consider this part only, right? So if this is my original tetrahedron, right, so it has A, B and C, right? So what I will be doing is, I'm first taking the midpoint between the first edge, right? So the first edge is A and B, right? So P1 of I, this particular point is P1 of I. P1 of I is equal to A of I plus B of I divided by 2. So I'll be finding the midpoint, right? So again P2 of I. P2 of I is what? P2 of I is nothing but the midpoint between A and C edge, right? So AB, AC and BC. So a of I plus C of I divided by 2. Again P3 of I is the midpoint between B of I plus C of I divided by 2, because I have to divide the triangle, right? So that is why how I am dividing the triangle, by making use of the midpoint concept, right? So I am finding the midpoint of this and this, right? So three midpoints I will be finding, I'll be finding, right? So then I will be interconnecting them. So the output will be, once I divide it, once I find the midpoints, right? So you can see that I have divided my original tetrahedron into how many tetrahedrons? I have 4 tetrahedrons here, right? So you can see this is my first tetrahedron, I have second tetrahedron here, third tetrahedron and fourth tetrahedron, right? So like this, every time you are dividing your triangle, right? So you are finding the midpoint between each and every edge. A of I plus B of I divided by 2. So this is the first point, which is P1 of I. Then I have AC, which is A of I plus C of I divided by 2. Then I have point 3, which is B of I plus C of I divided by 2. So every time you will be finding 3 midpoints and you are dividing the tetrahedron. So your single triangle face is divided into how many tetrahedrons? It is divided into 4 tetrahedrons, right? So we have the m variable goes like this. If m is equal to 0, I will get my original tetrahedron. If the number of divisions is 1, right? So if m is equal to 1, that means how many tetrahedrons it will give? I will get the output as 4 tetrahedrons, right? So again, if I take m is equal to 2, right? So when I take m is equal to 2, what happens? Again, that particular tetrahedron, right? So those 4 tetrahedrons will be divided into further 4 tetrahedrons. This one single tetrahedron is divided into 4 tetrahedrons, right? So now if I take the second division, m is equal to 2 division, what happens? Now this tetrahedron will be divided into 4. So 4 plus this tetrahedron will be divided into 4. 4 plus 4, again 4, again 4. So 4 plus 4 plus 4 plus 4, right? So 4 times 4, which is nothing but I will get 16 tetrahedrons, right? So 4 plus 4 plus 4 plus 4 is equal to 16 tetrahedrons, right? So again, if I take m is equal to 3, what happens? Again, those 4 tetrahedrons will be further divided into 4, right? So that means we say that the number of divisions will be in terms of 4 to the power of m. 4 to the power of m. Those many tetrahedrons you will get it as the output. So now, right, so we have to divide the triangle. We will call the function because it is recursively dividing the triangle, right? So since it is a recursive function what we are writing, so we will write the divide to triangle. So divide to triangle. So now what we will do is, we have to consider the tetrahedrons. Now I have the tetrahedrons, right? So I'll be considering 3 points. You have to pass the 3 points, right? So A, P1, P2, comma, M minus 1, right? So you will be passing the 3 points because this is one vertex, right? So if I take this point, right? So again, P1 is one more point, again P2 is one more point, A, P1, P2, right? So this tetrahedron is what I'm talking about, right? So this is A point, A vertex, this is the point P1, which is the midpoint of AB edge, and this is the point P2, which is the midpoint of AC edge, right? So I will take A, P1, P2, which is my tetrahedron. I will divide the triangle. So divide the triangle A, P1, P2, comma, M minus 1, because every time you have to reduce your divisions, right? So M minus 1. Again, you have divide triangle for you will be considering this part of the tetrahedron, right? So C is the point, right? So here what is the point for AC? AC means it is point P2. So C P2. For BC, what is the point? It is P3. So C P2 and P3, right? So C P2 P3 comma M minus 1. Again we will be considering the next tetrahedron, right? So what is the next tetrahedron I have? That is the point B, right? So this is the point B, right? And I have the point which is P3, right? So P3 is nothing but the this particular point which is the midpoint of B and C. So B P3, right? And one more point is P1. So P1 is nothing but the division of AB, right? So I will be taking the B P3 P1 and I will be dividing the triangle, right? So like this you have to keep on dividing the triangle, right? So we are not considering the middle tetrahedron. Why we are not considering the middle tetrahedron? Because the concept of 3D Sierpinski gasket or fractal geometry itself tells that the central triangle is removed and each of the other three are treated as the original, right? So we will be remaining, actually we will get how many tetrahedrons? We will be getting 4 tetrahedrons, but the center part of the triangle is removed. That is the concept of fractal geometry. Every time you are going for divisions, right? So the middle part will be removed and the remaining tetrahedrons will be considered, right? So that is why in the first case I have considered the tetrahedron which is the A with A vertex. This is my point P1, right? So of the edge AB, this is the point P1 and the edge AC, the point is P2. So A, P1, P2, M minus 1. Right. So again, one more tetrahedron, which is if I take C vertex, this is my AC. For AC, I have the point as P2. So C, P2 and for BC, I have the point as P3, right? So C, P2, P3, comma, M minus 1. So this is one tetrahedron. I'm calling the divide triangle function here, right? So one more tetrahedron which I'll be considering is B, right? So what is this point? This point is P1. This point is P3, right? So B, P3, P1, comma, M minus 1, right? So you have to leave your the innermost triangle, which is the concept of your fractal geometry, right? So that is why the divide triangle function is called only for 3 tetrahedrons. The middle part of the tetrahedron will be deleted, right? So if M is greater than 0, we have to do this, we have to call the divide triangle function recursively. Else what we'll do, if M is equal to 0, we are just calling the triangle function. So else triangle ABC, because if M is equal to 0, we will get only original tetrahedron. That means we are not dividing, the number of divisions are 0. We are not dividing the tetrahedron. If at all M is equal to 1, then we are dividing the tetrahedron, right? So this is your divide triangle function. Now coming to the next function is a tetrahedron, right? So now I have to draw that particular tetrahedron. So in order to draw the tetrahedron, right? So the basic tetrahedron has how many faces, right? So it has 1, 2, 3 and 4 faces, right? So we have to draw the triangles here. Four triangles we have to draw, right? So in order to draw the tetrahedron, I'll be using the first we have to select the color, right? So because we have to differentiate between the faces of the tetrahedron, so that is why I'll be using the function gl color 3f, right? So which color I'm selecting? Red color. So gl color 3f, right? So red color, which is 1.0, 0.0, 0.0. This is RGB color values, right? So if I write here 1.0, that means I'm selecting the red color. So once you select the red color, you have to call your divide triangle function, right? So you will call the divide triangle function. So red color part is this particular part. What are the vertices we have? V of 0 is the first vertex, V of 1 is the second vertex, V of 2 is the third vertex. So V of 0, V of 1, V of 2, comma, M. M is for the number of divisions, right? So next, GL color 3F. GL color 3F, which color I have selected here? RGB, right? So one more color, which is green color, right? So green color is selected for divide triangle. I'll be calling for the vertices, which is V3, V2, V1, right? So V3, V2, V1. That means my bottom face will be in green color, right? So V3, V2, V1, comma, M. Then I have my this part of the triangle, which is blue color, GL color 3F, 0.0, 0.0 and 1.0. This is my triangle, right? So what are the vertices involved here? Vertex 0, vertex 3 and vertex 1, V of 1, right? So V of 0, V of 3, V of 1, comma, M, right? So and finally GL color 3F, I'm using 0.0, 0.0, 0.0. That means black color, right? So this black color is vertex 0, vertex 2 and vertex 3, comma, M, right? So like this you have to you have to draw your tetrahedron. The next function is my display function, right? So inside the display function, I have called GL clear. So I have to clear the color buffers and the depth buffer. Why I'm using depth buffer here? Because it is a 3D, right? So whenever we go for 3 dimension, right? So we have to consider our Z axis, and when you are considering your Z axis, you have to include your depth buffer, right? So in order to reset or the clear the buffer, right? So for hidden surface removal is nothing but your Z axis, right? So whenever you are considering your Z axis, we have to consider the depth buffer bit. So initially I'll be clearing all my buffers. Next, I'll be loading the identity matrix, because you know any computer graphics calculation is matrix multiplication only. Whatever you do, any transformation, any rotation, any translation, whatever you do, it is actually matrix multiplication. So that is why I have to initially load my identity matrix, right? So then I'm calling my function, which is a tetrahedron of n, right? So you will be calling the tetrahedron function. So this tetrahedron function, right? So the tetrahedron of M, what you are calling this tetrahedron function, intern calls which function? It calls the divide triangle function. So the divide triangle function intern, it will call which function? It will call the triangle function, right? So like this the flow goes. So you are drawing the tetrahedron. So GL flush is basically used to force the activation of all the OpenGL functions, right? So this is our display function. The next function what we have is my reshape function, right? So why we are using reshape function here? Because initially my output window will be small. So if at all I increase my output window, right? So my output should my output should occupy my entire monitor screen, right? So in order to have that, so it should vary with my screen, right? So in order to have that, I'm making use of reshape function, right? So we have used this reshape function in our cube program also, right? So both the third lab program and fourth lab program, we have used the reshape function, right? So the same way here also we'll be using the reshape function. So in the reshape function, first we have to make use of our GL viewport, right? So GL viewport, because we have to set our viewing parameters, so it takes four arguments. So this is xmin, ymin, xmax, ymax, right? So because xmin is 0, xmax is width, right? So ymin is 0 and ymax is height. This is width and height of my viewport. Next, GL matrix mode, GL underscore projection, right? So you have to include your projection matrix, because I have to view in ortho, right? So I'm making use of orthogonal projection. So GL matrix mode, GL underscore projection. Next, GL load identity, you have to reset the matrix to its default state, right? So now we have to, for reshape function, we'll consider our width to height, right? So if W is less than or equal to H, if width is less than the height, that means width is more. So I'm drawing like this, right? So rectangle. If height is greater than width, means I will get a shape of a rectangle which is in the vertical shape, right? So if W is less than or equal to H, I'll be calling my GL ortho. So GL ortho will take how many parameters? It takes 6 parameters, right? So this is -12 or -20, anything you can write. So this is your left value, this is your right boundary, so this is your bottom boundary. The first part is bottom, the next part is a top boundary, this is far and near, right? So it takes 6 arguments. This is left, right, bottom, top, far and near. So I will write it here as -12.0 plus 12.0. Left and right ends we will define, then -12.0 into whenever W is less than or equal to H, right? So you will write your bottom and top as H divided by W, H by W, right? This is far and near values, right? So next are else GL ortho, right? So whenever you have your W is greater than H, at that time you have to change your left and right, because your column will be your screen will become like vertical rectangle, right? So that is why you have to change your left and right position. So here it is H by W, means when it is else part, you have to take it as a W by H, right? So this we have already done. Next, I have here my bottom, I have my top, then I have my far and near values. Then I will set the model view parameter. So GL matrix mode, GL underscore model view, right? So because we have to perform the transformation in terms of model view, right? So then I will call the function as glut post redisplay, right? So why we want post redisplay? Because if at all you change the width, right? So now you are making the screen big, so your tetrahedron also will look bigger, and it will be set to the entire screen size. If at all you are making your screen as a small, means again the tetrahedron should fit into that, right? So GL post redisplay the same tetrahedron what you are displaying, right? So the last function what we have here is the main function. So we know that the main function consists of two arguments, that is argc and argv. Argc is the argument counter, argv is the argument vector, right? So the first variable what we have to take the input here is the number of divisions. That means how many divisions you want for your tetrahedron. So read that variable. The variable is n. N is the number of divisions here, right? So there we will this n value whatever we have taken, that will be copied to m variable, right? So if at all you want to write it as m, you can write it, right? There is no problem. Next, first step is what we have to initialize our glut. So in order to have glut initialization, we'll call the function glut init ampersand argc comma argv. This is for initialization of your glut. Next, glut init display mode, right? So we have to set the display mode. So glut underscore single, I'm using single buffer here. Glut underscore RGB, because I'm using three colors, red, green and blue color model. RGB color model is what I'm using. Then I have glut underscore depth because I'm making use of the Z axis here. Next, glut init window size, right? So the size of my window is 500 comma 500. Glut create window, right? 3D gasket. The name of my window is output window is 3D gasket. GL clear color, right? So my background color is initially set to white, right? So on a white screen, you will get your output. Next, glut reshape function you are calling, right? So this is your callback functions. Glut reshape func my reshape, right? So the first call will go to the reshape function. Next, you have glut display func of display, right? So you'll be calling your callback function display. So this display function in turn calls the tetrahedron function. This tetrahedron function in turn calls the divide triangle function. The divide triangle function in turn calls the triangle function, right? So and finally you will get your output like this. If the number of divisions are 0, that means you are not dividing the tetrahedron. You will get the output in this manner. When the number of divisions are 1, means every time my tetrahedron will be divided into 4 tetrahedrons. You have to remember this. Every time a triangle will be divided into 4 tetrahedrons, then what is the concept? Forget about the middle tetrahedron. You have to delete the inner triangle and you have to consider the remaining 3 triangles and perform the division, right? So this is the output for number of divisions as 1. So as the number of divisions increases, right, so your division, the tetrahedron will also be further divided, right? So glut display func of display, right? So finally we have to enable, because by default the Z axis will be disabled. So in order to make use of this glut underscore depth, right? So in order to use the depth buffer, we have to enable the depth buffer, right? So GL and enable, we have to make use of the constant GL underscore depth underscore test, right? So if you enable, then only you'll be able to make use of the depth buffer, right? So finally glut main loop, because it is similar to our get ch function, right? So where we want our output to be seen on the display screen. So this completes your 7th lab program, right? Hope you are clear with the output and how this program works. So this is our 3D Sierpinski gasket. Thank you.